Welcome back to this next video in the playlist on Galois theory. So in this video, I'm hoping to prove the very famous result, the non-existence of the Quintic formula, and indeed a formula for any higher degree polynomials roots in any characteristic zero field. So please do have watched the previous video in the playlist on solvability by radicals, because we're going to use the result of that here. So I'm just going to state that result that we developed in the previous video, and then we'll go from there. So what we showed is that if the field f is characteristic 0, then a polynomial little f being, and I'm going to abbreviate, solvable by radicals over f, the big F, the field f, it occurs if and only if the splitting field of little f over big F is finite solvable, which I'll abbreviate to FS for short. We're now going to take this and use it to prove the non-existence of the Quintic formula. So firstly, let's just think about what it would mean to have a formula in our field. So we've got our field f, which is characteristic 0. If there were a formula for all degree 5 polynomials, and we'll do this for just degree 5 at the moment, but the argument completely works. At the end, I'll generalize it for all degrees higher as well. So if there were a formula in this field that gave you the roots of all degree 5 polynomials, you know, within the algebraic closure f bar, if there were a formula that gave you the roots for all of those polynomials, what would that mean? So it would mean, and this takes a bit of thinking about, you're going to have to potentially pause the video and think about this, but it would mean that all of those polynomials, so all little f of degree 5, so degree little f is equal to 5, it would have to be the case that every single one of them was solvable by radicals over not just f, but over the smallest subfield of f that contains all of the coefficients of the polynomial. So if our polynomial f is something like a5 x to the 5 plus a4 x to the 4 plus all the way down to a0, where the ai's are in the ground field, then these are the coefficients of the polynomial here. There is some smaller subfield of my field f which contains all of those. So it would be the rational numbers, which any subfield of this is going to have to contain the rational numbers because it's characteristic 0. But it would be the rational numbers adjoin a0, a1, a2, all the way up to a5. So this smaller subfield containing all of the coefficients, the polynomial is going to have to be solvable by radicals over that field. And this would have to be the case for all polynomials, all possible polynomials at degree 5. They would have to be solvable by radicals over their smallest subfield containing the coefficients, if it were the case that the formula exists. Why? Because what is a formula? Like, if I have a formula, the formula would have to be something like this. It would have to involve just the coefficients of the polynomials. I'll also allow it to involve rational numbers. So, for example, it can have halves and a thirds in. So if you look at Cardano's formula, the one for cubic equations, it contains like a half and a third. But really, to contain all rational numbers, all I have to do is allow it to contain 1 and 0. So well, I need to say more before I say that. So I'm going to allow it to contain the field operation. So it can contain plus, minus, multiply, and divide. So I'm assuming, you know, minus and divide are understood to mean taking additive and multiplicative inverses respectively. It can also involve radicals, and it can involve 1 and 0. So it could be something like this, you know, square root of a0 squared plus a1 squared plus a3 to the 3 plus a4 to the 5, the fifth root of that divided by 2 plus a0 plus a1. This would be plausible, or we could have over 5 there. Why am I saying that to involve all rational numbers, so, you know, a half, a third, all the rational numbers, why is it enough to say it just involves 1 and it can just have 1 in it? Because 2 is just 1 plus 1. A fifth is just divide by the multiplicative inverse of 1 plus 1 plus 1 plus 1 plus 1. So I could rewrite this term here as this. So it's enough to say it contains the field operations, it contains extracting radicals, and it contains 1. It's allowed to contain 1. The moment it contains all the field operations and it's allowed to contain 1, then it can contain any rational number. So that's my definition of the existing a formula. There would have to be something like this that's allowed to involve the coefficients of the polynomial, the rational numbers, and then extracting roots. But you know, if the roots were expressible in this formulaic fashion, then this is precisely to say that all of the roots would be in, you know, it would be inside a radical extension. Things of this form are going to be inside radical extensions of indeed the smallest subfield that contains the roots of the polynomial. Sorry, not the roots of the polynomial, the coefficients of the polynomial. So if we go back to this polynomial here, if this formula, so let's say for my characteristic zero field, if there was a Quintic formula that worked for all degree 5 polynomials, then it would work for this polynomial, and it would mean that the roots of the polynomial were something like this. Once you put into the formula the coefficients of the polynomial, they look like this, which means they're going to be contained inside a radical extension of this field, this smaller subfield of f that contains all of the roots of the polynomial. So that is what it means, what it would mean for there to be a degree 5 polynomial in my field capital F. It would mean that all degree 5 polynomials are solvable by radicals over the smallest subfield of F that contains all the coefficients of the polynomial. So how then am I going to show that there cannot exist such a formula for any characteristic zero field? Well, the rational numbers sits inside any characteristic zero field. So if I can find you a degree 5 polynomial with coefficients in the rationals, then this smallest subfield that contains all the coefficients would be just the rationals. So if I can find you such a polynomial with coefficients in the rationals that is not solvable by radicals over the rationals, and I'll show that it's not solvable by radicals by showing that its splitting field is not a finite solvable extension, i.e. its Galois group is not solvable, then that polynomial that I have found will be a valid polynomial in any characteristic zero field because of this, and therefore there can't exist a Quintic formula for any characteristic zero field because it wouldn't work on such a polynomial that I'm found. So I'm now going to find this polynomial for you. So my favourite example of one, and you know, remember this polynomial, is x to the 5 minus 4x to the 4 plus 2. And I like this because it's the easiest one to justify why it doesn't work. So this is a degree 5 polynomial. It's an integral polynomial, but it's certainly a polynomial with coefficients in the rationals. And I am going to show you that this polynomial is not solvable by radicals over the rationals. And the fact that it is not solvable by radicals over the rationals will mean that in any characteristic zero field there cannot exist a Quintic formula, because such a Quintic formula would not be able to work on this polynomial, and this polynomial is a valid polynomial over any characteristic zero field because the rational sits inside any characteristic zero field. Okay, you might have to map these onto what they are actually equivalent to in your field. Say you were using different symbols for these elements, God only knows why, but there is an isomorphic copy of the rational numbers sitting inside any characteristic zero field, and therefore there's an isomorphic copy of this polynomial in any characteristic zero field. So how am I going to show then that it's not solvable by radicals over the rational numbers? Well, I'm going to show you that its Galois group is not finite solvable. So the Galois group of this polynomial, which will denote Galois, or indeed the Galois group over the rational numbers of this polynomial. So remember, we're trying to show that it's not solvable by radicals over the rational numbers, so we need to show that its splitting field over the rational numbers is not a solvable extension, is not a finite solvable extension. So Galois group over the rationals of x to the 5 minus 4x to the 4 plus 2. Just in case you're not used to this notation, this is just a shorter, kind of cuter notation for the Galois group of the splitting field over the rational numbers of this polynomial, x to the 5 minus 4x to the 4 plus 2 over the rationals. So it's just a shorthand. So I'm going to show you that the Galois group of this, and when I say show, I'm not going to go into the full details. There are parts of the group theory that I will omit, or I will give you a sort of hand-wavy sort of, this is how this could be done, but we won't. There's one proof that I'm going to sort of like wave my hands at a little bit. You'll see where it comes up. So we're going to show that the Galois group of this is S5. Show in quotation marks. There is a bit that I'm going to leave as an exercise in group theory, or I will give you hints as to how it could be done. So the Galois group of this is S5. Now, it is a fact from group theory that if a group is solvable, then all of its subgroups are solvable. That's not too difficult to show. I won't do it in full, but I'll just sort of talk to you about how that would be done. So if you've got a group that's solvable, so that means that there is this chain of subgroups, ascending chain of normal subgroups. So the trivial subgroup H1, then H2, then H3, all the way up to Hn, which is equal to the whole group G, and we'll call the trivial subgroup, we'll call that H0. And each of these quotients, so hi quotiented out by hi minus 1, is abelian. So there exists this ascending chain of subgroups inside your solvable group such that all of the quotients are abelian. That's the definition of solvable. So if I now take any subgroup of it, so what should I call that subgroup? So we'll just call it G bar. So G bar is a subgroup of G. It doesn't necessarily need to be proper. I mean, it's trivial if it's improper, but we can let it be improper. So how do I know that this is solvable? Well, I need to find an ascending chain of normal subgroups inside G bar that also obeys this property that the quotient is abelian. And you know, what are you going to take? Obviously, you're going to take your starting one, and you're just going to intersect it with G bar. That's all you can do. There's nothing else really plausible to do. So you'll have H0 intersect G, which is just going to be, sorry, G bar, that should be, which is just going to be the trivial subgroup of G bar, and then it's going to be normal inside H1 intersect G bar, which is going to be normal inside H2 intersect G bar, etc., all the way up to the final one, which will be Hn intersect G bar. And you just need to justify why each of these remains normal, which I might just try and do. So let's say if we've got hi intersect G, why is it the case that hi minus 1 intersect, sorry, this should be G bar, hi intersect I minus 1 intersect G bar is normal inside hi intersect G. So if I take an element here, let's call it A, take an element here, let's call it B, I need to prove that BA, B inverse, is an element of hi minus 1 intersect G bar. So because hi is because hi minus 1 is normal inside hi, and because B and A are certainly, you know, A is certainly in hi minus 1 and B is certainly in hi, so I can say immediately that this is inside hi minus 1, but also because A and B are both inside G bar, when I compose BA, B inverse, that's also got to be inside G bar, and therefore I get this. So that proves that each one, that this is a ascending chain of normal subgroups. Then the harder bit, you have to argue why hi intersect G bar, quotiented out by hi minus 1 intersect G bar, why that is a abelian group. How are we going to do that? I think probably the best way to go is, again, to prove that the commutator of, as we did a very similar thing. In the previous video, we showed that if the group is solvable, that quotients of it are also solvable. Here we're showing that all subgroups are solvable, but there I struggled with this part of the argument as well, and eventually decided that the best way to do it was to prove that the commutator of the group was inside the thing that we're quotienting out by. So I think probably that's the best strategy again. So let's just attempt this. So if I take, again, A and B inside HI intersect G bar, then I need to prove that the commutator of A and B, so two general elements inside that, I need to prove that the commutator is inside HI minus 1 intersect G bar. So because my elements are general, if I prove this, then I've proven that a general commutator of two elements is inside this subgroup. Hence, the entire commutator subgroup is inside it. And we know then, a fact that I haven't proven, but I'm assuming you know from group theory, which is that if a normal subgroup contains the commutator subgroup, then the quotient will be abelian. And in fact, it's an if and only if. If the quotient is abelian, then the normal subgroup must contain the commutator subgroup. So how can I do this? So because these are certainly in HI, and because HI quotiented out by HI minus 1 is abelian, I can therefore conclude that the commutator of A and B is an element of HI minus 1. So this is looking very hopeful. In fact, this looks as though it's going to be quite easy. I'm quite pleased with this. This commutator subgroup trick is excellent. Like, trying to do this, you could probably argue this with potentially an argument involving the isomorphism theorems, but this is far better, far simpler. So also, because both of them are elements of G bar, because they're in that intersection, then this write out the definition of what the commutator of A and B is. It's A inverse B inverse AB. So if A and B have to be in G bar, A inverse and B inverse have to be in G bar, and therefore the composition of all these elements has to be in G bar. Therefore, the commutator is also in G bar, ergo it's in HI minus 1 intersect G bar. So there we go. That's how we can simply prove that these quotients are abelian. So what we've just proven is that if a group is solvable, then all subgroups of it are also solvable. So this proves then that S5 can't be solvable because one of the subgroups of S5 is A5, and it's a famous fact from group theory which I'm definitely not going to attempt to prove here. I think I do actually prove it in one of my videos in the playlist on group theory, although I made that playlist about potentially 10 years ago now, so I can't remember exactly, but this is a famous fact that is proven in all undergraduate group theory courses, that A5 is an insolvable group. So that means that S5 can't be solvable, because if it was, then A5 would be forced to be solvable, and we know that A5 is not solvable. So actually, I would just say a little bit more on this. The famous fact actually that I think most undergraduate courses prove is that A5 is simple rather than insolvable, but because they haven't necessarily gone over the definition of what a solvable group is, because it's not really relevant in initial undergraduate group theory, and it's relevant once you come on to Galois theory. But if you try to do it in a first course in group theory, it's kind of an unmotivated definition that you might not really appreciate. Why on earth would I care? So they generally prove that A5 is simple, but that means that A5 contains only one normal subgroup, which is not one proper normal subgroup, which is the trivial subgroup, and it's a non-abelian group, A5. So this is your only ascending chain of normal subgroups that you have in A5, and this quotient is not going to be abelian, because the quotient is going to be A5 itself, which is non-abelian. So that proves that A5 is not solvable, and therefore S5 is not solvable. Therefore, the fact that this polynomial has Galois group over the rational numbers S5 proves that it is not solvable by radicals over the rational numbers. So how then do I know that that polynomial does have Galois group S5? So this is beautiful, but this is the part where I am going to wave my hands a little bit. So firstly, the first bit I'm not going to wave my hands. I'm going to wave my hands at the group theory. I'm going to wave my hands so that I'll tell you what the fact from group theory that I'm not going to prove properly is. It is that if you go to S5 and you take a transposition, so an element that swaps just two of the elements of the set of 5 elements, and you take a 5 cycle and you put them in. So let's say if I had the transposition 1 2 and I had the 5 cycle 1 2 3 4 5, and I generate the subgroup of S5 containing those two, you can immediately conclude what that subgroup is. It is forced to be the entire group. Once you have a transposition and a 5 cycle in your subgroup, it's forced to be the entirety of S5. This is a fact from group theory that I will attempt to give you a little bit of a hand-wavy explanation as to how you would prove this, but it's a bit of a painful argument of just having to consider, like, it's a bit sort of combinatorical. You just have to think and think and think about how you would construct every possible transposition. So I'll come back to that. So this is kind of a fact from group theory that I'm going to assume. As long as you're happy with that, I will explain everything then. So a fact from group theory then is that if you have a transposition and a 5 cycle, then your subgroup of S5 that generates, and it's any transposition in any 5 cycle, so these were just 2 random ones, 2 nice ones indeed, but you could have picked any 2 other transposition. You could have picked any transposition here, so I could change this to 3 4, it would still work. I could change it to 5 1, it would still work. Similarly, you could change the 5 cycle to any other 5 cycle and it would still work. Any transposition and 5 cycle generate the entirety of S5. That is a fact from group theory, well-established fact from group theory. Okay, so now back to the sort of Galois theory bit. So why is it the case then that this thing's Galois group is the entirety of S5? Well, the way we're going to do it is by showing that there is a transposition in this thing's Galois group and there is a 5 cycle in this thing's Galois group. So let's start with the explanation for why there's a 5 cycle in its Galois group. So let's just write the polynomial out again. X to the 5 minus 4x to the 4 plus 2. So it's irreducible, firstly, by Eisenstein with the prime 2. So it's an irreducible polynomial. I'll write this like this. So it's an element of the irreducible polynomials with coefficients in the in the rationals. I mean, strictly by Eisenstein, it's irreducible over the integers, but then by Gauss's lemma, it's irreducible over the rationals. And the Galois group of it has to, this is a fact from Galois theory. The Galois group of this polynomial has to permute the 5 roots. It has to map the roots onto other roots. So all of the field automorphisms in this Galois group, they are just permutations of the 5 roots. And, the moment you decide where the roots of the polynomials are going, that completely determines the entire automorphism of the splitting field. So there's these 2 ways of thinking about the Galois group. You can either think of it, the better way of thinking about it is that it's the group of automorphisms of this splitting field that fix the ground field of rational numbers. But the equivalent way of thinking about it is that they are all just permutations of the 5 roots, and that specifying where the 5 roots are going is enough to specify where the entire field, every element of the field goes. It determines it. So there are those 2 equivalent ways of thinking about the Galois group. But because it's a permutation of the 5 roots, it's therefore a subgroup of S5. That's the crucial bit. So the Galois group is going to be a subgroup of S5, and now I want to prove to you that it has to contain a 5 cycle. So this happens because of the fact that that this polynomial is irreducible. So because it's irreducible, it means that it's monic as well. I've chosen it so it's monic. So it is the minimal polynomial for the 5 roots. And then this next argument actually latches on to the most powerful part of Galois theory, the beast in the back, that the underlying magic that underlies the entirety of Galois theory, which is that if 2 elements of a field have the same minimal polynomial, then they are algebraically equivalent, and furthermore, in the splitting field of that minimal polynomial, in the splitting field of that minimal polynomial, this thing here, they will be Galois conjugates. That's really the central, most important part of Galois theory, that all the roots of an irreducible polynomial are Galois conjugates, i.e. there is an automorphism that sends each one of them onto each other one of them in the Galois group. That's the magic of Galois theory. That, you know, that this minimal polynomial, that it splits into, that if you were to take one root, let's call it alpha, and you were to take all of its Galois conjugates, so x minus sigma alpha, or in fact, and you were to go over all the different Galois conjugates, that this would give the minimal polynomial, that this is the minimal polynomial, and that therefore all the roots of the minimal polynomial are Galois conjugates to one another, i.e. there is an automorphism that sends this one alpha onto all the other ones. You know, there's a sigma for this one, then there's maybe some sigma 2 here that sends you onto this other one over here. This is the magic of Galois theory. So, how do we now use this? So, if you think now about the group action, so if you think about the Galois group over the rationals of x to the 5 minus 4x to the 4 plus 2, acting on the set of 5 roots, so let's call them alpha 1, alpha 2, all the way up to alpha 5. So you've got all of the automorphisms down here in this column, so you might have sigma 1, sigma 2, etc., all the way down to sigma n, where n is the degree of the splitting field over the rational numbers. Then, if I were to go down this column for alpha 1, or indeed down the column for any of the other 4, then every single one of them appears in here somewhere. So alpha 2 will appear here somewhere, alpha 3 will appear here somewhere, alpha 4 will appear here somewhere, alpha 5 will appear here somewhere, alpha 1 will appear up there if we let sigma 1 be the identity automorphism. So the point is that the orbit under the Galois group, which I'll just denote G, so that G equal the Galois group, the orbit of any one of the roots is going to equal the entire set. So it's going to equal the set containing alpha 1, alpha 2, all the way up to alpha 5. Now, why is this useful? Well, we now employ the orbit stabilizer theorem to say that the cardinality of the orbit times the cardinality of the stabilizer equals the cardinality of the group. So in particular, the fact that this is 5 means that 5 must divide, 5 divides the order of the group G, or the cardinality of the group G. And this is a crucial fact. Now we use Cauchy's theorem to say that therefore there must be an element of order 5 inside the group. So Cauchy's theorem says that if you have a prime which divides the order of the group, then there is an element in the group of order equal to that prime. So 5 is a prime, it divides the cardinality of the Galois group of this polynomial. Therefore, by Cauchy's theorem, there is an element of order 5 inside this Galois group here, which is a subgroup of S5. Now, what are the elements of S5? Well, there are transpositions, there are 3 cycles, there are 4 cycles, like so, there are 5 cycles, this one being an example, there are double transpositions, like that. There are elements that are a 2 cycle composed with a 3 cycle. Are there any more elements? No, I think that's everything. These are the only elements. This element, this sort of element, is going to have order 6. This element is going to have order 2. This element's going to have order 5. This element's going to have order 4. And then you can fill in the final ones. The point is, the only elements in S5 which have order 5 are going to be 5 cycles. Therefore, I instantly know that there must be a 5 cycle in my Galois group now. So that's a powerful thing to know. Now all I need to do is prove that there's a transposition in it also, and then I'm done. I know the Galois group by my theorem that I'll try and justify in just a moment has to be the entirety of S5, and then I know S5 is insolvable, and therefore this polynomial is not solvable by radicals over the rational numbers. So why do I know it contains a transposition? So we're going to use a little bit of analysis here, which is a bit naughty in algebra, but analysis is a powerful tool. We have to sometimes admit that. So don't worry, we're not going to use any sort of advanced analysis. We're going to actually use a school-level argument which could be made rigorous with basic real analysis, but I'm not going to bother making it rigorous. So I'm going to basically argue that this polynomial x to the 5 minus 4x to the 4 plus 2 has 3 real roots and 2 complex roots. And then I'm going to argue that complex conjugation restricted to my splitting field is then going to be a automorphism, a Q automorphism of my splitting field, and it will then just permute the 2 complex roots, swap them round because they're complex conjugates of one another, whilst fixing all of the real roots, and therefore it will correspond to a transposition, and therefore my Galois group will contain a transposition. So why do I know this polynomial contains 3 real roots and 2 complex roots? Well, this is the reason I picked this one, because in reality, this argument, you can construct your own polynomials now that are insolvable over, or are not solvable by radicals over the rational numbers. All you need to do is pick one that's irreducible, and you can do that by Eisenstein, and then you just need to find one that has 3 real roots, and you can do that just by either graphing it, go onto Desmos and graph it, or as you can do, well, graphing is probably the best way, or making it rigorous, as I will justify in a little bit with the intermediate value theorem and turning points, this sort of theory. So, the reason I picked this one, though, is just because it's so easy to graph. I don't need Desmos. So if I consider the polynomial x to the 5 minus 4x to the 4, then this factorizes into x to the 4 x minus 4. I can easily graph that now. So you have to know what degree 5 polynomials look like, but basically they look like degree 3 polynomials. This one is just going to look like, so it's going to come down like this. It's going to cross at 4, and then it's going to go back up, touch at 0, and then go like this. So you can see this could be a degree 3 polynomial here. It's exactly the same picture. When you draw degree 5 polynomials, they often do just look like degree 3 polynomials. I mean, they can be more complex. Some of them might, degree 3 maximum looks like that, whereas degree 4 can have 4 turning points. Degree 3 can only have 2 turning points. So degree 5 can be more complex. They can end up looking, I think, like that. You see now it's got like 4 turning points. But this one doesn't. It only has 2 turning points, so it looks just like degree 3. How do I know it has to look like that? Well, because I know it has to be infinity up here and be negative infinity down here, and then it has to have just 2 points where it crosses the x-axis, and so this is really the only way this can happen if you think about it. So I know if it actually crossed at 0 and didn't just touch at 0 and then turn, then it would end up having too many intersections with the line y is equal to 0. So it's got to look like this. And then all I need to do is sort of like find out like what its value at 1 is, and I could do that, couldn't I? Like, at 1 it's going to be negative 4 there, you see, just by plugging in 1 into here. Oh no, sorry, I can't do basic maths. How embarrassing. Minus 3, it's going to be minus 3. Let's just check my arithmetic. 1 to the power of 5 is 1. Minus 4 times 1 to the power of 4, so this is minus 3. So now if I just add 2 onto it, you can see that I'm just going to lift this up by 2, and what's it going to become? It's going to become like this. It's still going to cross down there, because at 1 it's now going to be negative 1, and then it's going to go up like that. So I'm now going to have 3 points where it crosses the x-axis, sorry, the y-axis, no, it's crossing the x-axis, and therefore it's going to have 3 real roots. So that's the reason I chose that polynomial, because it's easy to graph. If you don't believe my little argument here, then you could go on to Desmos and graph it for yourself. How would you make this rigorous with basic real analysis? Well, you prove that this polynomial has only 2 turning points. You'd find where those turning points are, and then you'd just have to show that down here it's less than 0, then it moves to being above 0, and then it moves back to being below 0, and then it moves back to being above 0. So you just have to work out its value at 4 carefully chosen points, and then because it has only 2 turning points, the only thing that it can have been doing in the in between is turning twice, so it can't have more intersections with the y-axis, because otherwise it would force it to have more turning points than 2. And then of course we're also using the intermediate value theorem here as well. We're saying that a polynomial is continuous, and therefore the fact that it's above 0, for example, here, and below 0 here means that it must cross the x-axis. There must actually be a value where it is 0 in between. So, basic real analysis, but you don't really need that. You can just stick it into Desmos and convince yourself. But strictly speaking, of course, we should formally justify it with real analysis. Okay, so that means that my polynomial here has three real roots and 2 complex roots. Now there is a famous automorphism of the complex numbers. So if you go to the Galois group of the complex numbers over the real numbers, then this is isomorphic to C2. So there's the identity automorphism, and then there is complex conjugation, which is often abbreviated to tau. So that's an automorphism, the complex numbers, that fixes the real numbers. If you take that automorphism and restrict it down to the splitting field over the rational numbers of x to the 5 minus 4x to the 4 plus 2, then it is going to still be an automorphism of my splitting field. Now you might worry, like, how do I know that it is mapping things in here to things in here? What if it's mapping it to something outside it? But that can't happen, because it has to map all of the roots. It has to restrict to being an automorphism of this subfield, because this subfield is normal, because it's Galois. So this is a subfield of the complex numbers, but it's not just any old subfield. If I took the subfield, the rational numbers adjoin the cube root of 2, then that wouldn't be a normal subfield. In fact, that's probably not a good example. But if I took the rational numbers adjoin cube root of 2 zeta 3, so the primitive third root of unity is what I mean by zeta 3, e to the 2 pi I divided by 3. This would be a subfield of the complex numbers. If I apply this automorphism, complex conjugation, to this subfield, it would not restrict down to being an automorphism of this subfield, because it would map this onto a different subfield. It would map it onto the cube root of 2 times zeta 3 squared, which is a different subfield. These two are not equal to one another, even though they're isomorphic to one another. So it will map it on something that's isomorphic to it, have no fear about that, but it won't necessarily map it onto itself, because this subfield isn't a Galois subfield, it's not normal. All the roots of this element's minimal polynomial are not inside it, but this subfield is a Galois subfield, it is normal, and therefore when you restrict an automorphism of a larger field down onto a normal subfield, then it restricts to being an automorphism of that subfield. That's a general fact from Galois theory. So this complex conjugation is going to restrict to being a field automorphism of this field. It will fix the rational numbers, therefore it will be an element of the Galois group. I'm not going to write out its full name, I'll just call it G. The Galois group of the splitting field of this over the rational numbers. And what's it going to do? It's going to map the 2 complex roots. It's going to swap them round. They're going to be complex conjugates of one another, those 2 complex roots. And therefore, it's going to swap them round. And therefore, whilst fixing all the 3 real roots, and therefore there is going to be a transposition in my Galois group. So this is the way that I can conclude that there has to be a transposition in here. And now I use what I've said, which is that once you've got a transposition and a 5 cycle, it's immediately forced to be S5. So quod erat demonstrandum now. That's the end of the proof. That does it. This polynomial is not solvable by radicals over the rational numbers, and that proves that there cannot exist a Quintic formula in any characteristic 0 field. So we've got 2 more things to do. Firstly, I just want to try and give you a little bit of justification as to why, once you contain a transposition and a 5 cycle, that forces you to be the entirety of S5. And then I want to tell you how you can just generalize this argument to any degree beyond degree 5. So, and I'm going to do that in the cheapest way possible. Why is this true? So if you want to show that if you take a transposition and a 5 cycle, that it generates the entirety of S5, the way to do it is you need to show that all of the transpositions are forced to be in this subgroup generated by these two elements. Because once there are all of the transpositions are there, then it forces absolutely all the elements to be there, because all the elements can be written can be broken down into a composition of transpositions. You can achieve absolutely every element by composing a bunch of transpositions together. That's what we do when we, for example, study the concept of odd and even permutations. We study how you can break all the other permutations down into compositions of transpositions, and how this isn't unique, but the parity of the breakdown is determined by the element. So whether you need an odd or even number of transpositions to make that element, that is well defined, and there's no way, if you've broken it down into an even number of transpositions, let's say 8, there's no way to write it as a product of 9 transpositions, or indeed 13 transpositions, or any odd number of transpositions. And that's then the concept of the parity of a permutation, whether a permutation is odd or even. So hopefully you're familiar with the idea that all permutations can be broken down into products of transpositions. So once you prove that all transpositions are there, that proves that it's the entire group. So how do you show that all transpositions are there? Well, you basically take your transposition here and you try and build other transpositions by conjugating it by the other element that you've got here. And you use the fact that conjugation in the symmetric group is very beautiful. It basically, if I conjugate this by this element, it changes these two elements onto what they're mapped onto by this one. So it would send 1 to 2 because this is mapping 1 to 2, and it would send 2 to 3 because this maps 2 to 3. So it would turn it into the transposition 2, 3. And you would have to do this the right way round. And off the top of my head, I don't completely remember which way round it has to be. Whether I think we could work it out. Yeah, I think it needs to be. If we call our transposition tau and we call this sigma, I think it would need to be this way round. So it would need to be sigma tau sigma inverse rather than sigma inverse tau sigma. I think that would then turn, in this specific example, it would turn 1, 2 into 2, 3. So, what you do, if we take our example, so without loss of generality, you can assume the transposition is 1, 2. Then with loss of generality, we can assume that the 5 cycle is 1, 2, 3, 4, 5, and we then have to argue why it would work for an arbitrary 5 cycle here. But just for the sake of demonstrating, let's let it be that one. So if I call this sigma and this tau, then if I do sigma tau sigma inverse, I get 2, 3. So that's a new transposition. Excellent. Now I can compose sigma with itself, and I get a new 5 cycle. I get 1, 3, 5. 5 would then go to 2, I think, and 2 would go to 4, which would then go to 1. So this is sigma squared. I could then conjugate tau by sigma squared now, and it would send 1 to 3, and it would send 2 to 4. So I then get the transposition 3, 4. And you can go on like this. In fact, probably the easier way to see it is you now take this one and conjugate it by sigma, and you then get the same one as this one here. Because we'd just be doing sigma inverse, which is the same as what I've just done by conjugating by sigma squared. So in this way, you can see I would be able to get 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1. So that's a whole bunch of them. And now what I can start doing is conjugating each of them by these other transpositions that are forced to be in here. So if I conjugate 1, 2 by 2, 3, I'm now going to get 1, 3, because it's not going to change 1, but it's going to send 2 to 3. If I conjugate, what else can I do? If I now conjugate 1, 3 by 3, 4, I'd get 1, 4. If I conjugate 1, 4 by 4, 5, I'd get 1, 5, which I've already got, so that's not very useful. But you see how I'm just getting more and more and more? And basically formalizing this argument, thinking it all through very, very carefully. And I have done it once in my life, thought this through incredibly carefully to make sure that it actually does work and that I can argue, and I do understand how with any old 5 cycle there you can get every single possible transposition from it. And then I haven't been bothered to ever think about it again in my life. But this is how you would do it. You just have to think very, very carefully, think of all the different transpositions you have to get, and think how you, with whatever 5 cycle you have here, it would be possible to get all of them in this way. Okay, so that's the basic idea. I'm not going to try and formalize that because it would require too much thinking. But this, if you don't want to have to think through that for yourself, you can just accept this as a accepted fact in group theory that has been proven very, very well, that once you have a transposition and a 5 cycle, that immediately forces it to be the entirety of S5. Okay, but obviously we're mathematicians, so we want to understand everything. So think through this for yourself and work out why this works, why you can get every single transposition here. So now, where to next? So now I want to prove that we can generalize this. So I want to prove that there won't be a formula for any higher degree either in any characteristic zero field. So it's quite simple. I just need to find, again, a polynomial of degree n. So if I want to prove that there does not exist a formula for degree polynomials equal to some n, which is a natural number greater than 5, greater than or equal to 5, then all I again need to do is find a polynomial over the rationals that is not of that degree that is not solvable by radicals over the rational numbers. Because again, if there existed a degree n formula, or a formula for all degree n polynomials, what that would correspond to is it would mean that every single degree n polynomial with coefficients in the field would have to be solvable by radicals over the smallest subfield of the field F that contains all of the coefficients of that degree n polynomial, just exactly like we had up here for degree 5. It's just now there are more coefficients because it's a higher degree than 5. But the same thing holds true. So if I can therefore find a polynomial of my degree n, so we're imagining n is some fixed number greater than or equal to 5, if I can find a polynomial over the rationals that is not solvable by radicals over the rationals, then that proves that that degree n formula cannot exist, because if it did, well, it can't possibly work for this polynomial, because the smallest subfield containing the coefficients of the polynomials is the rationals itself, because I've said all of the coefficients are in the rationals. And it's not solvable by radicals over the rationals. So how do I do this? Well, this is the cheap way of doing it, by the way. So I'm just going to take my polynomial that I've already got, x to the 5 minus 4x to the 4 plus 2. I'm going to multiply it by whatever amount that I still need. So x to the n minus 5. So this polynomial now is a degree n polynomial. What's its splitting field over the rational numbers? What's its Galois group going to be? Well, it's going to be the same as the Galois group of this bit, because this bit's just got zeros as its root. So that adds absolutely nothing. So the splitting field of this polynomial, splitting field over the rationals of x to the 5 minus 4 x to the 4 plus 2 times x to the n minus 5, this is the same as the splitting field over the rationals of x to the 5 minus 4x to the 4 plus 2. And we know that this is not a solvable extension of the rational numbers. This has Galois group S5 over the rational numbers, and therefore is not a solvable extension. And we know that that means, therefore, that this polynomial, because its splitting field is not a solvable extension, that it is not solvable by radicals over the rational numbers. And we're done then. This proves there cannot exist a formula for degree n for the roots of a polynomial of degree n in any characteristic zero field. So I think we'll leave it there. Thank you for watching. So I had finished the video and was preparing to upload it, but then I felt a little bit guilty about not giving you the proper explanation as to why, when you have a transposition in a 5 cycle, that generates the entirety of S5. So I've come back and I'm going to properly prove this. So what I said was right. With loss of without loss of generality, we can assume the transposition is 1, 2, because, you know, all the transpositions are equivalent, so we're just going to pick one, and the argument will work for any one of them. This equivalent argument will work for any one of them. There's nothing that I'm doing here that is specific to it being 1, 2. It could have equally been 2, 3. I then picked the 5 cycle 1, 2, 3, 4, 5, and that was with loss of generality. So I'm not going to do that now. So without loss of generality, what I'm going to say is I have some 5 cycle, and I'm going to put 1 in position 1 because, you know, 1 appears in the 5 cycle somewhere, so I might as well have it in position 1 because I can just move everything around so that 1 is in position 1. You know, if I've got like 2, 3, 4, 5, 1, then I can, this is equivalent to 1, 2, 3, 4, 5. So I can always take my 5 cycle and rewrite it so that 1 is in position 1. So that's fine. So I've got now 1 alpha, beta, gamma, delta, where alpha, beta, gamma, and delta are 2, 3, 4, and 5, but we don't know which one's which. Now, 2 appears somewhere in this 5 cycle. So, for example, it might be that gamma is 2 over here. Now, by composing the 5 cycle with itself enough times, I can get it so that I will have the 5 cycle 1, 2, and then what Greek letters shall I use now? Let's have zeta, xi, and theta, where zeta, psi, and theta are 3, 4, and 5, but I don't know which one's which. So again, I'll just explain why I can do this, because, you know, if, for example, 2, if I start with my 5 cycle like this, and 2 is in position, if alpha's 2, then I'm already done, I don't need to make any changes. If beta's 2, then I just need to take this element and square it, compose it with itself, and then I'll have that 1 is being mapped onto 2. So I'll have something that I can write in this form, like so. If gamma is 2, then I just need to do this element multiplied by itself 3 times. And if delta is 2, I just need to do it to the power of 4. So the point is that by taking powers of my original 5 cycle, I can get a 5 cycle of this form where I've got 1, 2, and then the other 3 things in some order that I don't know. So I've now got my transposition and a 5 cycle like this. Now, if I call this transposition tau and I call this 5 cycle sigma, then if I do tau, sigma, tau inverse, what am I going to get? It's going to produce me 2 zeta here, because 1 is going to go to 2 and 2 is going to go to zeta. This is how conjugation works in the symmetric group. This is a famous fact about conjugation in the symmetric group, how if you take an element and you conjugate it by another element, then you just need to know what the look at the element in cycle notation that you're conjugating by, in this case sigma, and it's just going to, you just need to replace the elements in the cycle notation for your original element with what they're being mapped onto by the element that you're conjugating by. I have a video explaining this somewhere in my group theory playlist. So now consider sigma squared tau sigma to the negative 2. So now I'm just conjugating this element, 2 zeta, by this. What's it going to be sent on to? Well, 2 is going to zeta, zeta is going to xi, and I can keep going, and you can see what I'm going to get is I'm going to be able to get every single one of these. If 2 elements are next to each other in this 5 cycle, I'm going to be able to get that transposition. So overall, I'm able to get the transpositions 1, 2, 2 zeta, zeta xi, xi theta, and theta 1. All of these I'm going to be able to obtain by conjugating tau by powers of sigma. So this next one, xi theta, would be sigma cubed tau sigma to the negative 3. So that would be xi theta. And then sigma 4 tau, sigma to the negative 4, this would be theta 1. So now you can see that I'm making progress here. I've got quite a few transpositions. My next move is going to be to get all transpositions involving 1. Now I've already got 2 of them, this one here and I've got this one here. I only need 3 more, because if I can get all transpositions involving 1, then I'm done. I can get all transpositions from that, and I'll show you how in just a moment. Let me convince you that I can get all transpositions involving 1. So if I now conjugate this element 1, 2 by this transposition here, 2 sigma, and that's going to produce me 1 zeta. Sorry, 2 zeta, not 2 sigma. That's going to produce me 1 sigma, because 1's going to be fixed by conjugation by this element, and 2 is going to go to zeta. Then, if I conjugate now 1 zeta by this next element here, zeta xi, then what am I going to get? I'm going to get 1 xi, and then what other one do I need? So I've already got 1 theta. Is that... Oh, this is actually... Oh, I thought there were 5, but actually there's only 4, isn't there? Because, you know, you've fixed 1, and then there's only 4 things that you can put in. So there we are. I've now got all transpositions involving 1. There's only 4 of them. Now, how can I then get anything? Because, you know, if I want any old transposition, so a transposition involving something here and something here, then I've already got the ones involving 1, so let's assume that neither is 1, so I don't want 1 in either position. So let's say I want sigma xi here. How do I get it? I mean, I've already got zeta xi, sorry. I've already got it here, so it's kind of pointless, but let's say I'm trying to get one that I haven't already got. So let's say I want to get 2 xi. The way that I would do it is just by conjugating this one by this one, because what would that do? It would swap 1 for xi, it would fix 2, and therefore I would get 2 xi. So I hope you can see that by the fact that I've got all of the transpositions involving 1, it then means that any other transposition that you want that doesn't involve 1, so any of the other transpositions aren't going to involve 1, because I've got all the ones that involve 1, any of the others I'm going to be able to get by picking the 2 elements that involve those 2 elements that I want in my transposition. So if I want AB in my transposition, then I just pick 1A and 1B, and then I conjugate one by the other, and it doesn't matter which one you conjugate by which, you'll get the same thing. That's how I can get then any transposition. So that's an argument then as to how I can get any transposition once I've got this, a 1 transposition and a 5 cycle, and ergo, once you've got all transpositions, you've got everything. So that then proves that a transposition and a 5 cycle does indeed generate the whole of S5. So now we will finish. Now that I'll sleep easier now I've explained it properly.